Hello, and welcome to Friday STEAM with the Warren County Library System. My name is Sandy Roberts, and I'm the Makerspace Coordinator for the Warren County Library. Each week we bring you science, technology, engineering, art, and math all mashed up into one with some fun experiments that you can do at home and a little bit of science that you can take with you. Sorry that we got started a little bit late today. I'm not sure what's going on. This computer doesn't seem to like to work with Facebook very well, so I apologize for that delay again. It's a new computer from the library, and it's just giving me a little trouble, technology trouble. We'll get it all sorted out, though. All right, so if you've been following along the last couple of weeks, you know that we have been learning all about the states of matter. So we've talked about solids, liquids, and gases, and we've talked about what atoms and molecules are, what the states of matter are, the difference between physical and chemical changes, and we're going to review all of that today. But today we're going to move on to some of the rare types of states of matter that are out there. Things like Bose-Einstein Condensers, plasmas, Non-newtonian fluids. These are a little different than your normal states of matter, and they're really exciting and interesting. And then, of course, we have a couple science experiments to do. Please note, I am following along on my phone, so if you have any questions at any time, I am happy to answer them. Here are the supplies you're going to need for today. All right. We are going to need some heavy cream, okay? This actually is best with dairy, but I have actually tried it with coconut, and you can often get it to work. So you need heavy cream. You're going to need a clean jar with a good top. You're going to need some marbles that are also washed and cleaned. We do not want dirty marbles. And we are going to need a bowl and a spoon or some sticks, and cornstarch, and water. So I've got my pitcher of water. Okay, so those are our supplies. So if you want to work on that while we kind of get started talking about the science, you can do that. Or if you're watching later, feel free to pause the video and go and get your supplies now. Okay, let's get started with our, we're still having some trouble. Let me just convince it that it does want to see our presentation here today. Why are we being difficult for me? I apologize. Like I said, new computer, and sometimes it can be a little challenging. Let's see, do we have it now? One more try. If not, we'll just, here we go. I think we've got it now. There we are. Okay. Second or third time's the charm, right? All right, so other states of matter. Let's start with a little review on atoms and molecules. So atoms are the building blocks of all matter, and matter is all the things that you can taste, touch, and feel. So basically the universe is made up of matter and energy. We are matter. Oops, sorry, touched the mic there. So you can think of it as the Legos that build everything. Each Lego is a little bit different. Each atom is a little bit different. They all have different qualities and characteristics. So an atom of oxygen is very different from an atom of gold. And that's all because they have different numbers of protons in their nucleus, okay? And these are the positively charged particles in the nucleus of an atom. Whizzing around outside those are, I should mention, also in the nucleus are the neutrons. They don't have a charge at all. They are not like that. They are basically the packing peanuts of the nucleus to keep the protons from getting too close together. Because if that happens, the protons will push away from each other because like charges repel. And if you've ever used magnets and tried to stick the two positive sides together, you felt that push back. It's the same kind of thing happening in an atom. Whizzing around outside that nucleus are electrons. And electrons, when they move around, can join with other atoms. When that happens, we get molecules. Okay, so when atoms bond together, they make molecules. And those molecules are completely different from the atoms they came from. So the one example I tend to use is, actually, this is a great one. If you take the flammable gas hydrogen and the flammable gas oxygen and merge them together, you get water, which puts out fire, which is funny, right? Think about that. So you get all kinds of new compounds this way. You can make millions of different molecules from the 120 or so atoms and elements that we have so far discovered. Okay, so moving on, all these things come together to make matter. And that is, like I said, everything that's around you. These atoms define the matter as anything that has mass, so that's literally the number of atoms in something, and takes up space, has volume, okay? So you have mass, which we experience as weight, and you have volume, you take up space. Now, let me explain a little bit of that. I want to use my example. When we talk about matter, we often talk about its density, okay? So, for example, if I gave you a giant garbage bag of feathers, that has very little mass, taking up a very large volume. So it's not very dense, it's easy to carry around all day. If I gave you that same big garbage bag filled with rocks, rocks have a lot of mass, okay? And in that very same exact space, it's going to be a lot harder to carry them around all day because they're much more dense, okay? You've experienced volume, I'm sure, if you've ever gotten into the bath and seen the water rise on the bathtub, okay? That's proof that you take up space, that you have volume. All right, matter can change from one state to another. Basically, if you add energy to it, usually in the form of heat, it will go from being a solid, ice cube, for example, it will melt, okay, it will hit the melting temperature with the heat that is going into it, and it will become a liquid, water. Add more heat, it will hit its evaporation point, and it will evaporate and become a gas, water vapor. Now, say that gas rises, it cools off, it's going to hit its condensation point, okay? That gas is going to condense back into a liquid. Now, if it gets even colder, if we remove even more heat, take more heat away, those little tiny molecules and atoms will stop moving around and they will become a solid again when it hits its freezing point. I want to make sure that we kind of go over this because we're going to be talking about a special version of condensation today. And what's important to understand is that when something is in a solid, it's usually in a pretty rigid form. It can't just take on any shape. The molecules inside are pretty much just hanging out on the couch, watching Netflix. They're not moving around a lot. In a liquid, they're moving around a little more. Maybe they're, playing a video game or dancing to some music. Now, when you get to a gas, that's when they're running around like crazy. They have lots of energy. They're at a soccer game. They're at a basketball game. Okay? So that's really important because how much those atoms and molecules are moving really determines the state of matter. And how do they get that extra energy? Usually in the form of heat. More heat energy, more movement. Less heat energy, less movement. This is going to matter a little bit. Now, we also know that there are additional phases of matter, and that's what we're going to learn about in a little bit. We call these physical states. They're different from, so solids are always kind of hard and brittle. They have their shape. You can think of like a piece of wood, right? You could try to put a piece of wood to fit a cup, but unless you carve the wood, that's not going to happen. Liquids, on the other hand, you can pour a liquid into any shape cup, any shape container, and it's going to take the shape of that container. It's a special thing liquids do. Now, gases will do that too, but they don't stay. They aren't pulled down by gravity like liquids are, so they don't necessarily stay in the bowl. There's always that, have you heard the whole glass half empty, glass half full idea, that if you have a glass of water and it's filled up halfway with water, is the glass half empty or is the glass half full? Well, what scientists say is it's always full, just it's got some liquid and some gas because the air is on top of the liquid. So to a scientist, the glass is always full. Kind of optimistic that way. Alrighty. Now, a physical change, as I said, is when you have something like a state of matter change. The molecules move around and they have a physical change. This is very different from a chemical change. Like when I mentioned taking hydrogen and oxygen to make water. That actually changes the material. In a physical change, water is still water. It doesn't become something new and mystical and magical just because the ice cube melts. It's still got those properties. And that's important. Okay, we're talking all about physical changes here, not about chemical changes. That's a big difference. Okay, so let's talk about some of the different states of matter. Plasma doesn't really happen here on Earth, but a lot like gases, they move around a whole lot. The difference is, in a gas, the atom stays basically together. The electrons, the protons, and neutrons stay basically together. Maybe a couple of electrons might move away to like form new bonds, but the atoms stay as atoms. Not so in a plasma. Okay, not so in a plasma. In a plasma, all the electrons are just free. They're all wandering around. They're meeting up with each other. They're meeting up with all the other atoms. And that means that that nucleus is hanging out on its own too. They're disassociated. They're all flowing around together. So they're very high energy states of matter. Okay? And because of this, any tiny bit of energy added will result in even more energy being pulled in. So we don't find these too much on Earth, but we do find them in stars. Our entire sun is a plasma, so it flows like a fluid, flows like a gas, moves like a gas. It's got the low density of a gas, but it's highly, highly energized because those electrons are just moving everywhere. See, this is something important. Electrons are actually what's responsible for electricity. The movement of electrons is what actually generates electricity. Those tiny little particles that we can't see, when they're flowing, that's what gives us electricity. So imagine if you have something 1,000,000 times the size of the Earth made out of this highly energized plasma where the electrons are just running all over the place all the time. That's a lot of energy. That's a lot of energy. And that's why plasmas are special. We also see them in, and I put electricity, that shouldn't be electricity, lightning. Sorry, typo. Lightning is basically a very quick forming plasma when the electrons in the sky during the right conditions actually charge one another and you get a lightning bolt. You see it a little more commonly with these plasma globes that you can find in the store that's actually using an electrical charge to generate that tiny, tiny little bit of safe amount of plasma. So plasmas are really important, but they're really hard to generate because they take so much energy to make. Now, we have learned how to harness them in smaller doses, and that's why we have plasma screen TVs now. So you get nice, bright pictures, right? Lots of energy going in, but they have to keep that film really, really thin so that you don't end up with any of the heat or other issues that a plasma can cause. All right, next, Bose-Einstein Condensers. This is not a natural state of matter like solid or liquid or gas or even plasma. Bose-Einsteins are actually made. We call them BECs, and it's a state of matter that was invented, created in 1995. That was within my lifetime, by the way. I was in college when this happened. So two scientists, Cornell and Weinman, actually developed the first ones, and what they did is they took rubidium, which is a pretty big molecule, a pretty big atom, okay, an element, and they cooled it, and they cooled it, and they cooled it, and they got it so cold, so condensed that the atoms were almost not moving at all anymore. So they got it to almost the coldest temperature you can possibly achieve. And when that happened, with certain substances, they found something interesting happened. The atoms didn't just stop moving, they clumped together. And they joined together. And instead of being separate atoms anymore, they all clumped together into like one big blob where they were sharing everything. A little bit like the plasma, but instead of being super high energy, it was super low energy. Now you might be saying, why would you want to do that? Well, first, to prove that you could have the opposite of a plasma. Okay, not going to lie, that's part of it. More than that, though, if we can get a material like this to be stable, we can use it as a superconductor. We can use it to transmit data, because when you don't have all the movement of the atoms, you don't have energy going out to that. You don't have your signal being corrupted. You can use this for a lot of different things. We could make super fast computers with these materials that would be highly efficient using every little bit of electricity to the absolute maximum. And that's why they're studying these kinds of materials. This is ongoing research. It is cutting edge research. I know that they are looking at now being able to do this with things like helium and hydrogen, which are some of the smallest atoms out there. And if they can get them to be stable and not take a ton of energy to make in the first place, that's part of the challenge, because you have to get them so cold, it takes a lot of energy to cool them off. But if we can get that working, we can make thin slices of this, put them in our computers, and have super fast, super energy efficient computers. And our wireless networks and our internet could also benefit from this and work even more efficiently. So it's really interesting science. I will share a video in the comments section if you want to learn more. And now on to my personal favorite, Non-Newtonian fluids. Newton was a scientist who figured out important things like our laws of motion. And he figured out that mass and speed, or acceleration, determine the amount of force behind something. In other words, if the tractor trailer is moving really, really fast, it has more force than, a scooter going really slowly. I think you can kind of, which would you rather get hit by, right? Right. So Newton figured out a lot of these sorts of things, and some of his laws were the laws of viscosity, which we're going to talk about in a moment. But non-Newtonian fluids don't follow the rules of viscosity, okay? And they can actually change their viscosity depending on if a force is applied to them. Now, that's not normal. If you drop water on the ground, it doesn't suddenly become ice, right? It's still just water. Just because it was under a force doesn't mean that it changed its state of matter. But with non-Newtonian fluids, they can. Putting force on a non-Newtonian fluid actually causes it to change its viscosity and basically change a little bit of its state of matter, which is pretty wild. But they're actually pretty common. Ketchup, custard or pudding, honey, toothpaste, cornstarch in water, which we're going to do in a minute, paint, blood, melted butter, and shampoo are all non-Newtonian fluids that work this way, which is one of the reasons why when you try and squeeze the toothpaste out, you have to put extra force behind it. Because the more force you put, the less liquidy it is. Crazy, right? We're going to experiment with that in a minute. Let's talk a little bit about viscosity. So viscosity is just a property of any liquid or fluid that describes how fast or slow it flows. Okay? So a river flows pretty quickly. That's got a very low viscosity. It's really thin liquid. However, things like ketchup or peanut butter or shampoo or toothpaste, okay, are very thick. They have high viscosity. Okay? Some of this is due to just the properties of the atoms and molecules in it. Sometimes it has to do with how much oil there is, things like that. A lot of factors can affect viscosity. But viscosity is really important in the study of liquids. And if you have a parent who is a mechanic, I bet they can tell you all about viscosity because it's really important when it comes to the oil that we use in our car engines. So viscosity, these science terms aren't just for people in labs. This is everyday stuff that you need to understand. And I bet if you talk to a parent about the oil that they use in their car, traditionally, we used to have to change oils depending on how cold it was outside. Because if you didn't have the right viscosity oil in your engine wasn't going to work as the temperature dropped. All right, so we're going to experiment with some non-Newtonian fluids in just a moment. But in the meantime, if you want to learn more about this, Chem for Kids, I've mentioned before, great website, lots and lots of information on matter and chemistry. Crash Course Kids has a great YouTube playlist on matter, and they're really fun videos, usually pretty short. And of course, check the library for books. Go to warrenlib.org. We've got lots of great science books that you can check out. Okay. Let us switch to my other camera so that we can do our experiments. Okay, hello. Make sure this is as wide as I can get. I think it is. Alrighty, so our first experiment today is making butter. Okay, so we are going to use the properties of something like heavy cream to actually make a really fancy emulsion. Okay, and this does tend to have some of the properties of a non-Newtonian fluid. So to make butter, it's really very, very easy. You take nice cold as you can get it, heavy cream. Don't put it in the freezer, but nice and cold in the fridge. You put your heavy cream in, and you can put as much or as little as you want. I like to put a little bit of salt in there, so I get salted butter, or what we call sweet cream butter. Okay, a little bit, just a tiny bit, pinch. And then I put some nice clean marbles in. Technically, you don't need this if you don't fill your jar all the way, because we need agitation. We need to mechanically force the oil and fat molecules in here to create the kind of net that we need to make our butter. Marbles help that by making more agitation. Of course, the downside is then you have marbles in your butter. It's a personal choice. I'm going for quick. So in those go, and then the process is really easy. Agitation, mechanical energy. You shake, and you shake, and you shake, and you keep on shaking until you have butter. This will take a couple minutes. I'm not going to demonstrate it all right now. But if you get a friend, 10 minutes, 15 minutes, depending on how cold your cream was to start, and you're going to have butter. I will say it does help sometimes to wrap it in a towel so it stays cold while you're shaking. But I used to do this all the time with my students, and then we'd have nice bagels for breakfast. So it's actually really easy to do. It's really easy to make butter. If you were so inclined, you could use a mixer to do this, a big stand mixer or something like that. You don't have to do it by hand. But it's really fun to do, and it tastes really good. Fresh butter, good stuff. So that's how you make butter, an emulsion, and a non-Newtonian fluid. Now, onward to everybody's favorite, Oobleck, otherwise known as cornstarch in water. Cornstarch really is, in water, a fantastic non-Newtonian fluid. And what's really special about it is that when you apply force, okay, when you put pressure on it, basically, it will go from being very liquidy to getting more viscous and seeming like a solid. So you can like pick it up if you're holding your Oobleck tight, but the moment you let go, it drains out of your hands. So we're just going to go ahead and put some cornstarch into our bowl, and get my water. And you just want to add a little bit of water at a time. You don't want to overdo it. The smallest amount of water you can use is for the best here. You can also add food coloring if you want to. Now, here's the thing about doing this, and you will see it very soon, right away. Like you can even see how that's already forming the non-Newtonian fluid. It's hard to mix water into cornstarch because the more pressure you put on it while stirring, that energy of just stirring, actually makes it become more solid and more viscous. So that you can see already, it's becoming more solid simply by adding that liquid, or simply by applying that force, rather. So you add a little at a time, you keep on mixing and mixing and mixing, and you will see that, it's hard to pull it across, but the moment I stop pulling, it's liquidy again. Did you see that? Push, 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 and then liquid. It's really fun to play with. There's a great Dr. Seuss book that you can borrow from the library, all about Oobleck. And it's really fun to read and make this, and I like to dye it green so it matches the book. But this is really interesting to play with. You can also try things like really paying attention to honey and ketchup and other fluids like that, and see if they behave in the same way. One of the most fun things you can do with Oobleck, and I'm just going to zoom in so you guys can see this. One of the most fun things that you can do with Oobleck is in the summertime, you get a nice big, flat, low Rubbermaid container, fill it with Oobleck, and run across it. Because the pressure of your feet running is enough to solidify the Oobleck so you can stand on it for like just a millisecond. But you can see this is very liquidy. The moment I apply force, it hardens, and then when I stop, it goes back to being a liquid. You see that? So this is really fun to play with, and it's a great example of a non-Newtonian fluid. You can see right there. Hard, 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 let it go, back to liquid. You can, of course, if with your parents' permission, use this in your hands. It is quite a sensory experience. And that's how you make Oobleck and create your own non-Newtonian fluid. All right. That's about it for today. That is the last of our states of matter science. Next week, we'll be learning about coding as a STEAM activity, because next week is Computer Science Education Week. So if you want to get a little bit of the idea of how coding works, what it is, and why we care, tune in next week at 3 p.m. for that talk. And then after that, we're heading into the holiday break. So we will have a couple more Friday STEAMs, and then we'll be starting for the new year. If you have science topics that you would like to see covered during Friday STEAM, send me an email at sroberts@warrenlib.org. I would love to know what you want to learn about. All right, my name is Sandy Roberts. I'm the Makerspace Coordinator for the Warren County Library System. This is Friday STEAM with the Warren County Library, and I hope that you stay safe and stay healthy and have a wonderful weekend. Take care.